Sekejap, saya nak record sekejap. Dah start recording ke? Alright. Okay, bismillahirrahmanirrahim. Assalamualaikum and very good afternoon everyone. Welcome to today's collaborative teaching with guest lecturer session. So let us start our session with Kitab Al-Fatihah. Okay, today we have a very special guest speaker, Dr. Arif Mawardi Ismail, to share his lecture on Faraday's laws topic. Before that, let me introduce a little bit about our guest speaker. Okay, Dr. Arif Mawardi Ismail is currently working at University Malaysia Perlis UNIMAP as senior lecturer at Faculty of Electronic Engineering and Technology. He received his PhD in physics from the Penn State University, USA in 2018 and Master of Science from the University of Bonn, Germany in 2010. He is a dedicated and organized researcher who is eager to apply over a decade of formal training in experimental physics to real-world problem solving. He also has a vast experience in teaching electromagnetic theory in UNIMAP. Okay. So before we start, I would like to remind students the attendance form will be given at the end of the session. Okay. All right. Without further ado, please welcome our speaker, Dr. Arif. I pass the session to you, Dr. Arif.
Okay. Thank you very much, Dr. Robiatun, for the invitation and also for the very kind introduction. So let me share my screen. Boleh nampak tak, Doktor?
Saya boleh nampak.
Okay.
Pelajar boleh nampak ke?
Boleh.
Mouse cursor boleh nampak juga? Cursor tak nampak?
Nampak.
Cursor nampak.
Nampak. Okay. Okay. So thanks again, Dr. Robiatun, for the invitation and for the kind introduction. So my name is Arif Mawardi from UNIMAP. And the topic that I will be talking about today is Faraday's law. So I guess for the next 2 hours, right, Dr. Robiatun?
Yes, 2 hours.
Yeah, okay.
Plus minus.
Plus minus, okay, right. Okay, so from what I understood, so you have covered these 2 topics, electrostatics and magnetostatics. And so for these 2 topics, you will mainly be dealing with static cases. So you have static electric fields, which are created by stationary charge distribution. So this is the topic of electrostatic. And then for magnetostatic, so you were dealing.
Dr. Arif,
Yeah.
sorry for interrupting.
Yeah.
I just can see your first slide. I'm not sure the students can see your first slide or not. Oh. Students macam mana? Boleh tengok ke slide?
No.
No, Sekejap saya cuba.
No.
Saya cuba stop ya, macam mana? Stop sharing. Presenting, saya cuba share screen, share window.
Maybe share window.
Okay. Yang ni boleh?
Okay, nampak. Tapi
Okay.
kena view
Macam mana?
slideshow kot. Maybe kena buat slideshow.
Okay, sekarang slideshow.
Yes.
Yang tadi nampak juga? Kalau keluar.
Yang tadi nampak yang dia punya ni lah.
Ni, tepi ni.
Slides. Tepi tu.
Okay, tak apa. Okay, so yeah, so what from what I understood, so you have covered these two topics. So these two topics, in these two topics, you will mainly be dealing with static fields, static electric fields, and static magnetic fields. And so now, so I will talk about these time varying fields. So in this topic, so we will be dealing with fields that are varying with time. Yeah. So in other words, as time progresses, so these electric and magnetic fields are no longer static, so they are changing with time. So that is why in this notation here, so you will notice that, so in the previous one, we only have the electric field as a function of the coordinate r, whereas for the time varying fields, we have fields that are also dependent on time. Yeah. And so in this case, so in the case of time varying fields, so the electric fields and the magnetic fields, they are no longer separate entities. So they are now interdependent with each other. So in other words, whenever you have a time varying magnetic field, yeah, so a magnetic field that is changing with time, so that will produce an electric field. And the vice versa is also true. So whenever you have a time varying electric field, so that will produce a magnetic field. Okay, so one important phenomena in time varying field is called this electromagnetic induction. So what is this electromagnetic induction? So this electromagnetic induction is the production of an electromotive force in a conductor due to a changing magnetic field. Yeah, so this phenomena here is illustrated in this animation here. So I will try to explain this animation. So first, so we notice that, so here we have a conductor. Yeah, so this is conductor which is connected to an emitter to measure any current that is flowing in this conductor. And so you should also notice that this conductor is not connected to any power supply. So it is not connected to, for example, any battery. Yeah, so this is just a conductor, so in which a current can flow, and it is not connected to any power source. Yeah, and then here we have a solenoid, and then this solenoid is connected to some power supply or some current source that will that can cause current to flow in this solenoid, in this coil here. And then, as you can remember from magnetostatic, so whenever there is a current flowing in this solenoid, so this solenoid will produce a magnetic field. Okay, and then so you see here, so according to this electromagnetic induction, so whenever you have a coil, and then if this coil, so if it sees a changing magnetic field, a magnetic field that is changing with time. So as you can see in this animation here. So you can see here, so the magnetic field at this coil, yeah. So the magnetic field at this coil is changing with time. So whenever there is a changing, whenever a coil, a conductor, so if it is seeing a changing magnetic field, so what will happen is that, so there will be an EMF induced in this coil. So what is an EMF, electromagnetic force? So this electromagnetic force is something that can drive current in the conductor. Yeah. So this is what we are seeing here. So you see, whenever when this coil, when it sees a changing magnetic field, so there will be an EMF that is induced in this conductor, and this EMF then will drive current in this conductor. So even though this conductor is not connected to any kind of power source, so there will still be a current flowing in this conductor because there is a changing magnetic field seen by this coil. So that phenomena is called electromagnetic induction. So this electromagnetic induction only occurs when there is a changing magnetic field. So for example, if I stop, so if I stop here, so if the magnetic field is not changing, yeah, so even though the conductor, there is a magnetic field at this conductor, but because the magnetic field is not changing, so there will be no EMF that is induced in this conductor, meaning that there will be no current flowing in this conductor. Yeah, so according to electromagnetic induction, so an EMF is only induced in this conductor if, so the condition is that if there is a changing magnetic field at this conductor. So if there is no changing magnetic field, if there is just magnetic field that is not changing, so that will not induce an EMF in the conductor. Okay, so that is called electromagnetic induction. So it will produce an electromotive force. So this is something important in the topic of Faraday's law. Yeah, so it is called electromotive force that will be induced in this conductor, and then this electromagnetic force will then drive current in the conductor. So now we want to be more quantitative. We want to know how to calculate this electromagnetic force that is induced in a conductor due to a changing magnetic field. So that is so that is what is given by Faraday's law. So according to Faraday's law, so the induced EMF in a closed conducting loop is equal to the rate of change of the magnetic flux through the loop. So the formula, so in a mathematical form, so this is what Faraday's law looks like. So according to Faraday's law, if you have a closed conducting loop like this, yeah, so there will be there will be an induced EMF in the loop, and that induced EMF is equal to the rate of change of this quantity here, this symbol here. So this is called the magnetic flux through the loop. So I will explain what this quantity means. So this quantity here, which is called the magnetic flux through the loop, is equal to the surface integral of the magnetic flux through the surface of the loop. So the surface of the loop is this shaded region here. So this is what we call the surface of the loop, or to be more precise, the surface that is encircled or bounded by the loop. Or we can, so to loosely speaking, we can just call it the surface of the loop. So this is what this is how the magnetic flux through the loop is defined. It is defined as the surface integral of the magnetic field through the surface of the loop. Yeah, so this is the general definition of magnetic flux. Yeah, but in most cases, so we can just simplify this to be, so the magnetic flux. So this is repeat again. So this is the general definition of the magnetic flux through a loop. But for most cases, for most practical cases, we can just this integral here can be simplified as the dot product between the magnetic field and the surface area. Or sorry, the dot product between the magnetic field and the area vector. So this is how the magnetic flux is defined. And as you already know, the dot product here is defined as the magnitude of the magnetic field times the area of the loop times the cosine of the angle. So theta here is the angle between the area vector and the magnetic field vector. Yeah. So this is how the magnetic flux is defined. And now, according to Faraday's law, whenever this quantity changes, yeah, so there will be an EMF that is induced in this loop, and that EMF then will drive current in the loop. Okay, so now if we look at this relationship here, so if you look at how the magnetic flux is defined, yeah, so we can see that the magnetic flux here, so it depends on the magnetic field and also the area of the loop. Yeah, if you look at this definition here, so the magnetic flux depends on the magnetic field and also the area. So therefore, we can so there are several ways in which the magnetic flux can change. So the first way that the magnetic flux can change, so you can see here, so the magnetic flux depend on the magnetic field. So that means if the magnetic field is changing while the area is not changing, so that will cause the magnetic flux to change, because the magnetic flux depends on the magnetic field. So if the magnetic field is changing, so meaning that if we have a static loop like this, the area of the loop is not moving, and also the loop itself is not moving, but instead, if the magnetic field is changing, so if the magnetic field through the loop is changing, so that means the flux is also changing, and then according to Faraday's law, there will be an EMF induced in this loop. And then the second way that the magnetic flux through the loop can change is by having the area of the loop changing. Yeah, because as you can see from this relationship here, so the magnetic flux also depends on the area. Yeah, so that means, let's say if I can change the area of the loop. Yeah, so like this. So even though the magnetic field is not changing, so if the area is changing, so that means the magnetic flux through the area, through the loop will also change. And then according to Faraday's law, there will also be an EMF induced in the loop. Okay, or I can also make the loop moving like this, as we can see later. So in this case, even though the magnetic field is not changing, so if the area is changing, so that will also produce, that will also cause the flux through the loop to change, and that will also produce an EMF in the loop. Okay, and so there is also another way that the area can change. So that is by rotating the loop. So if you rotate the loop like this, so even though the area of the loop is not changing when you rotate this, but the direction of the area vector will change if you rotate it like this. If you rotate the loop like this, so the area vector of the loop will change. And that will also cause the flux through the loop to change. And so as a result, so there will also be an EMF induced in the loop. Yeah, so let me recap. So first, we can have a changing flux by having the magnetic field itself changing. Or we can also have a changing magnetic flux by having the area of the loop change, or by rotating the loop. And the third way is by having both, yeah, changing. So the magnetic field is changing and also the area of the loop is changing. So the area here, so let me repeat again. So the area here is just the area that is bounded by the loop. So if you have a circular loop, so the area is pi r square, pi times the radius of the loop, circular loop square. And so if we have a rectangular loop like this, so the area here is just the length times the width of the loop, rectangular loop. Okay, I guess let's look at a concrete example. Okay, so by the way, so if we have, for the first case, if we have a stationary loop which is placed in a time varying magnetic field, so the EMF that is induced in the loop is called motional EMF. Yeah, so this is what we are going to talk about next. Oh, sorry, not motional EMF. It is called transformer EMF. So if you have a stationary loop which is placed in a time varying magnetic field, so the EMF that is induced in the loop is called transformer EMF. So this is an example of a transformer EMF. So in this example, we have a circular conducting loop that lies in the z equal to 0 plane, and it has a radius of 0.1 meter, and it has an internal resistance of 5 ohms. And now this loop is placed in this time varying magnetic field. Yeah, so how do I know that this is a time varying magnetic field? So I know that this is a time varying magnetic field because if I look at this expression here, so B here, it depends on time. So that is how I know it is a changing magnetic field. Yeah, because it depends on time. So as time changes, so B will also change. And so as a result of that, because this loop, so it is lying in a changing magnetic field. So there will be an EMF induced in this loop, and that EMF will then drive current in this loop. So our task now is to determine the current that is induced in the loop. So the first step is we need to calculate the magnetic flux. Yeah. So remember, the magnetic flux is given by the dot product between the magnetic field vector and also the area vector. Okay, so the magnetic field is given here, and for the area, so the area, to calculate the area, we just use the formula for so this is for the area. So the area for this, so since this is a circular loop, so the area will be equal to pi times r square. So here we have 0.1 square. Okay. And then, so we also need to determine the direction of the area vector. So as you know, so in physics, area is a vector. So it has both magnitude and direction. Yeah, so this is the magnitude of the area vector. And as for the direction, so it is always normal to the surface area. So the surface area is like this. So that means the area vector is normal to the surface area. So it should be pointing upward. And then according to our coordinate system here, so that means the direction of the area vector should be A along the Z direction, because it is pointing along the Z direction. Okay, so now we have the area vector. We can calculate the dot product between the magnetic field vector and the area vector. So we then have 2t a z dot width. So the area vector is pi 0.1 square a z. Yeah. So this will then be equal to, I guess it is 0.02 t pi. Okay, we have pi, and then 0.1 square is 0.01. Yeah, and then 0.01 times 2 is 0.2. Then we still have t here. And then we have this dot product between AZ and AZ. So I guess as you can remember, so if you have the dot, so the dot product between the same unit vector is equal to, so the dot product between the same unit vector is just equal to 1. Yeah, so therefore AZ dot AZ is just equal to 1. So we are left with this expression here. So this then will be the magnetic flux that is going through the loop. Okay, so now that we know the magnetic flux, we can use Faraday's law to determine the EMF that is induced in this loop. So according to Faraday's law, so the VEMF that is induced in the loop is equal to the rate of change of the magnetic flux. So we have already calculated the magnetic flux. So we just need to substitute this. So this will be equal to 0.02 pi t. And then if we do this, so that will be equal to 0. If you take the time derivative of 0.02 pi t, so that will be equal to 0.02 pi. So this is the EMF that is induced in this loop. Okay. And so one thing I would like to point out here is, so you notice that in Faraday's law, there's a minus sign here. Ada soalan? Ada, okay. So in Faraday's law, there's a minus sign in front here. So we will come to what this minus sign means. But for now, when you calculate the EMF, you can just ignore this minus sign for the moment. Yeah, so I will come back to this, the meaning of this minus sign later. But for now, when you calculate the VMF that is induced in the loop, so we can just ignore the minus sign. Yeah, so therefore the voltage, the EMF that is induced in the loop is 0.02 pi V. And now in the question, we are asked to find the current that is induced in the loop. So to find the current, we can just use Ohm's law. So according to Ohm's law, V is equal to IR. So we have already calculated the induced EMF. So therefore, the current will be equal to, V EMF divided by R. So therefore, it is equal to 0.02 pi divided by the resistance is 5. So this will be equal to yeah, I don't know, I don't have my calculator here. So equal to some number. Yeah, sorry. Yeah, it will be equal to some number ampere. Yeah, I'm not so interested in the value, but just so the idea. So maybe you can calculate later what is the value. So to get the value, is just you can just simply use your calculator. So this is how we determine the current that is induced in the loop. So let me recap. So the first step is you need to determine the area of the loop. So remember, area is a vector. So meaning that it has a magnitude. So the magnitude is just the surface area of the loop. And it also has a direction. And the direction is always normal to the loop. And then once you know the area, you can calculate the dot product between B and A, which will give you the magnetic flux through the loop. And then once you know the magnetic flux, we can just use Faraday's law to calculate the EMF that is induced in the loop. And then to find the current that is induced in the loop, we just use Ohm's law. Okay, so now, so there will be a current induced in this loop, because this loop now it is placed in a time varying magnetic field. So there will be a current induced in this loop. So now the question now is, so in which direction so the induced current is flowing? So is it flowing in the counterclockwise direction, or is it flowing in the clockwise direction? So there are two possibilities. So the question now is, how do we determine the direction in which the current is flowing? Yeah, so to determine the direction of the current, so we need to use Lenz's law. So that is the meaning of the minus sign in front of the minus sign in this Faraday's law here. So what does Lenz's law say? So Lenz's law states that the induced current flows such that to produce a magnetic field that opposes the change in the induced magnetic field. Uh, so if you find it confusing, I agree with you, this statement. So I think let me try to explain this using this example here. So now we have a loop like this, yeah, and then we have a changing magnetic field. So how do I know that it is changing? Because the magnetic field here is dependent on time. And I also know that from this relation here, I also know that the magnetic field is increasing with time. So how do I know that the magnetic field is increasing with time? So I know that because, as you can see here, so the magnetic field here is directly proportional to time. So that means as time increases, the magnetic field will also increase. Okay, so therefore, let's assume, suppose that at time equal to 1, so the magnetic field is pointing up and it has this certain length. And then at some later time, yeah, so for example, at t equal to 2 seconds, so the magnetic field, because it is changing with time, it is increasing with time, so that means at some later time, so the magnetic field will increase in magnitude. So that means the arrow that is representing the magnetic field will become longer because the magnetic field is increasing with time. So now by looking at this, we can determine the direction in which the magnetic field is changing. So I repeat it again. So we need to determine the direction in which the magnetic field is changing. Or in other words, we need to determine the direction of the change of the magnetic field. Not the direction of the magnetic field, the direction of the change of the magnetic field. So as you can see here, so first, the magnetic field has this length, and then at some later time, it has this length. So therefore, the direction of the change of the magnetic field will be up, because it changes from this. So this is the head of the arrow. It changes to this position. So therefore, the direction of the change will be in this direction. So this is the direction of change. or magnetic field change. Okay, so the arrow, the green arrow here is the direction of the change of the magnetic field. So now, according to Lenz's law, so the current that is induced in this loop will try to oppose the direction of the change of the magnetic field, not the direction of the magnetic field itself. You have to determine the direction of the current using Lenz's law, you need to focus on the direction of the magnetic field change. So in this case, the direction of the magnetic field change is upward. So therefore, the direction of so the current that is flowing in this loop will try to produce a new magnetic field that is in the opposite direction as the direction of the magnetic field change. So therefore, and then if we use the right hand grip rule, so we will find that, oops, here. So your thumb here indicates the direction of the magnetic field that the current is trying to, the induced current that is the induced current tries to oppose. So according to this right hand rule, so in order to produce a magnetic field, a new magnetic field that is opposite to the direction of the magnetic field change, so the current has to flow in the same direction as your fingers here, which is counterclockwise. So that is how you determine the direction of the induced current using Lenz's law. Okay, so maybe one example, maybe it's not, you're still not clear. Maybe we can look at another example here. So here we have a loop, and this loop is placed in this changing magnetic field. So how do I know that it is changing? Because B here depends on time. Okay, and then if I look at this relationship here, so I can see that the magnetic field is inversely proportional to time. So that means as time increases, the magnetic field will decrease because of this inverse proportionality. Okay, so if I repeat the same procedure here, so at time equal to 1, suppose that, let me bring this here. So at time equal to 1, suppose that the magnetic field has, so initially the magnetic field has this length. And then at some later time, so we can see from this relationship that at some later time, as time increases, the magnetic field will decrease. So therefore, at some later time, so the magnetic field will, so the magnetic field vector or the arrow that represents the magnetic field vector will become shorter at some later time. So this is how the magnetic field is changing with time. So now from the sketch here, we can determine the direction in which the magnetic field is changing. So if you look at this sketch here, we can see that so the magnetic field is changing in this direction because it starts from here and it goes to here. So therefore, this is the direction of change, which is different from the direction of the magnetic field. So this is what matters. Yeah. So when we want to use Lenz's law to determine the direction of the induced current, so we look at the direction of change. So now that we know the direction of change, so according to Lenz's law, the direction of the induced current will be in the direction such that the induced current will produce a magnetic field that will oppose, that will be in the opposite direction as the direction of change. So therefore, in this case, the induced current will try to produce a magnetic field upward, which is opposite to the direction of the magnetic field change. And then if we use this right hand grip rule, so we can see that the direction of the induced current will be in this direction, which is clockwise. Yeah, so this is how we determine the direction of the induced current using Lenz's law.
Excuse me.
Yeah.
Can I ask a question?
Yeah, sure.
I still don't get why the example before the thumbs facing downwards and the example after the thumbs facing upwards. I cannot determine how to determine the induced current.
Okay.
Arrow.
I think I got your question. So in this example, so first, as I said before, so first we determine the direction of the change. So is this clear to you why the direction of change is in this direction?
Not really.
Not really in this direction. So um so it is in this direction because you see so first you see at t equal to 1, so the magnetic field has this certain length. Yeah. And then we know that the magnetic field is increasing with time. So because the magnetic field is increasing with time, so that means at some later time, so it will become longer. So far, can you follow me so far?
So the arrow will be given in the question later.
So this arrow you mean?
This arrow which show the t equal to 1 second and t equal to 2 second, that both of the arrow will be show in the question.
No. So from this one. So I just
From
take
this
one
one.
example. I just take one. So one. So just to represents all the magnetic field through the loop here. So you see all the magnetic field at every point on the loop is pointing upward. Do you agree with me?
Yes.
Yeah. So that is why I draw a magnetic field that is pointing upward.
All right.
Okay. And then because the magnetic field, we know from this relationship, we can see that the magnetic field is increasing with time. So that means if at time equal to 1 second, it has this length. So because the magnetic field is increasing with time, so at some later time, it will surely get longer. Right?
Right.
Yeah? Okay.
Yes, I agree.
Okay. So now, so the magnetic field starts at t equal to 0, at t equal to 1 second, this length, and at some later time, it will get longer. Okay, so from this, from these two magnetic field at different times, at 1 second and 2 second, so we can then determine the direction of the magnetic field change. Okay, so why do I draw an upward arrow here? Because, okay, maybe I can something like this. So this is at t equal to 1, and then at some later time it will become longer. So this is the direction of change. So this is the direction of the change in the magnetic field. Okay, so is this one clear to you? Why
Yes,
the direction
I'm clear.
of? Okay. Okay, so now we know the direction of the magnetic field change. Okay, so now according to Lenz's law, the direction of the current flow, the direction of the current that is induced in this loop is such that it will produce a new magnetic field that will be pointing in the direction opposite to the direction of the magnetic field change. So the direction of the magnetic field change is upward. So therefore the new magnetic field that the induced current will produce will have to point in the opposite direction, which is indicated by your thumb here, which is downward. So if you use your right hand and then you let your thumb pointing down, so you will see that your fingers are curling in this direction. So your fingers now indicates the direction of the induced current. Uh, okay, boleh nampak tak?
Boleh.
Boleh. Okay, so for this one, the same thing. We apply the same idea. Yeah, so except for this one, we know that the magnetic field is decreasing. So the magnetic field, how do I know the magnetic field is, why do I draw an upward arrow like this? Because the magnetic field, according to the question here, so I just take one example here, one particular magnetic field here. Yeah, so I know that the magnetic field is pointing upward at t equal to 1. And then at some later time, so it will decrease. So therefore, the direction of the change will be this direction, will be downward. Yeah. And then, so according to Lenz's law, so the current that is induced in the loop will try to will follow in a the direction of the induced current will flow in the direction such that it will create a new magnetic field that will be in the that will be in the opposite direction as the direction of change. So the direction of change is downward. So therefore the direction of the new magnetic field that will be produced by the induced current will have to be upward. And to produce an upward magnetic field, so the current has to flow in this direction according to your right hand grip rule. So is there any more question? So I hope this is clear. Ada soalan lagi tak?
Clear, Doctor.
Okay. So you can also apply the same idea here. So in this example, we just want to determine the direction of current using Lenz's law. So this require a little bit of extra imagination. So we can see here, so the magnetic field. Dr. Rabiatun, macam mana nak break ke?
It's up to you, Dr. Arif. If you want
Biasa-
to have a break, then it's okay.
Saya
How
okay.
many slide left?
Ada lagi banyak. Nak apa? 1 jam ke 2 jam?
It's up to you.
Okay.
I just follow your. If you want to have a break, 5 minutes break, then it's okay.
Normally, how do you do this? You just continue for 2 hours or you have a break in the middle?
No, normally I have a break session.
Oh, okay. So let's take a break. Biasanya berapa minit?
5 minutes is okay.
5 minutes. Okay. Yeah, sure. So
Alright.
yeah, so maybe we can continue at 3:55. So meanwhile, if you have any question, you can ask me. And also meanwhile, maybe you can try to determine the direction of the induced current for this example here. So we have a magnetic field that is pointing out of the page and it is decreasing. Okay, see you in 5 minutes. Okay, so let's continue. Boleh dengar? Cuba.
Boleh, boleh.
Okay, okay. So yeah, so this one maybe I will just give you the answer and then you can try this as an exercise. So I think it should be, so the direction, because the magnetic field is decreasing, so the direction of the magnetic field change will be into the page. So this is the direction of um, change of the, this is the direction of the magnetic field change, which is into the page. And then so to produce a new magnetic field that is opposite to the direction of the magnetic field change, so the current has to flow in this direction. Yeah, so maybe you can try this as an exercise to see whether you can get this one. So I think should be correct. So decreasing into the page, and then to oppose this, we'll have to flow in this direction. Right, yeah. So you can verify this, try to use Lenz's law to determine the direction of the induced current. So I have two more examples on transformer EMF, but I will not, because the idea is just the same. You start by calculating the area. Yeah, so the area for this one, if your loop is a triangular right triangle like this, so the area will be equal to um 1/2. I think for an area it will be, so 1/2 times 0.4 times 0.3. So this will be your area. So this will be equal to 0.06. Yeah. So you need this area. So to calculate the your magnetic flux. Yeah. So once you know the magnetic flux, you can just use Faraday's law to determine the induced EMF. And then once you get the induced EMF, you can just use Ohm's law to determine the current that is induced in the in the conducting loop. Yeah. So I guess it's the procedure is quite straightforward. Yeah. Okay. And also same thing here. Oh, I forgot to mention this. So far we have only considered a loop that is consisting of just one winding. Yeah. So if we have n windings like this, so if your loop has n windings and n turns like this, so all you need to do is so the first step is the same. You determine the area vector, and then once you know the area vector, you just calculate the magnetic flux by calculating the dot product between the magnetic field vector and the area vector. And then once you know the magnetic flux, so you can calculate the VEMF by using Faraday's law by taking the time derivative of the magnetic flux that you have calculated here. But here, if you have n turns, I forgot to mention this, so you just need to put n in front. So you need to multiply the time derivative of the magnetic flux by the number of turns. Yeah, so maybe I can do this real quick. So therefore your area is, so the area will be, so what is the radius? So the radius is 0.1. So therefore it will be pi 0.1 square. And the direction is along the Z direction. So the direction of the area vector is normal to the area, which is along the Z direction. And then, so your magnetic field is B not the uh, so B not 3A Y plus 2A Z, and then this is dot with the area. So the area is pi 0.1 square A Z. Um, yeah, so if you do this, so you need to expand this. So when you expand this, you see that for the first term here, so you have the dot product between different unit vectors. Yeah, so you have the dot product for the first time, for the first term here. If you expand this, so you have the dot product between AY and AZ. So as you remember, the dot product between different unit vectors is just equal to 0. So therefore, we can just ignore the first term here. So that means we will have B0T square times times 2. So B0T square times 2, and then times pi 0.1 square. Yeah. Okay. And then to calculate the EMF, you just need to multiply with the number of turns, which is 10, and then the time derivative of the magnetic flux, which is this quantity here. Yeah, if you take the time derivative of this, I guess. So this is just a calculation, you know. So I think you can do this. If you take the time derivative of this, you will get 2t. So this is just a matter of using your calculator to get the value. So I just want to highlight the idea of how to do this. Yeah. So first you calculate the dot product, and then here, if you have n turns, when you calculate the VEMF, you need to put this factor in front of the time derivative. Yeah, so I will not proceed. I think we can. So I hope you already get the idea. So it's just a matter of plugging all the numbers, and then use your calculator to find the value. Okay, so now I want to move on to the second kind of EMF, which is called the motional EMF. So in this case, so in contrast to the previous case, so in the previous case, we have a static conducting loop, and then we have a changing magnetic field. But here we have a static, in this case here, we have a static magnetic field. So the magnetic field is, which is not changing with time. And then we have a conductor that is moving in this static magnetic field. So when this happens, so when we have a static magnetic field and then we have a conductor that is moving in this magnetic field, so there will also be an EMF that is induced in this conductor. And this EMF then will drive current in this conductor. Yeah. So if you think about it, so this is also interesting because as you can see, this conductor is not connected to any power source, it's not connected to any battery, yet we can still have a current that is flowing in this conductor here, simply by having this conductor moving in a magnetic field. Yeah, so if you think about it, is this interesting and useful phenomena. Yeah, so it has many applications. So you don't need any battery. You just need to let the conductor move. that will induce an EMF that will then drive current in the conductor. So this the VMF that is induced in the conductor, so you can calculate this using this formula here. Yeah, so where in this formula, U here is the velocity vector, which is the direction in which the conductor is moving, and B here is the magnetic field, yeah, and then DL here is a differential element on the conductor or on the rod. So we will see an example of how to apply this formula here to calculate the induced EMF. So let's look at this example. So we have a magnetic field of 5 Tesla, and then we have a rod of this length, which is moving at 2 meters per second in the magnetic field. Okay, so now we are asked to calculate, now we want to calculate the EMF that is induced in the conductor here because of its motion in the magnetic field. So the first step is you need to determine all the quantities in this formula here. So first we need to determine the differential element. So determine the differential element, we can see that, so this is a differential element on the rod. So we can see that the rod is oriented along, so this is our coordinate system. We can see that the rod is oriented along the y direction. So therefore the differential element will be dy a y. Ay. So that's our differential element. And then we need to determine the velocity vector. So for the velocity vector, we can see that here, u is given here. So the speed is 2 meters per second. And then, so therefore the magnitude is 2. But we also need to write down the direction of the velocity vector. So we can see that the velocity vector is pointing along the positive x direction. So we need to refer to this coordinate system. So the velocity vector is pointing along the positive x direction. So therefore the direction is x. Okay, and then we need to determine the direction of the magnetic field vector. So the magnetic field vector is, so according to this, so it is pointing into the page. Yeah, so into the page means that the direction according to this coordinate system, so it is not along the x direction, it is not along the y direction. So instead it will be along the negative ax direction, and the magnitude is given here, which is 5 a z. Okay. Okay, so now that we have all these quantities, we can just substitute all these expressions into this formula here. So if you do this, we will first we need to calculate the dot product between the cross product between the velocity vector and the magnetic field vector. So this will be equal to, if we just substitute these two expressions here, we get 2a x times minus 5a z. Yeah. Okay, so this will be equal to minus 10, which is 2 times minus 5 is minus 10, and then we have the cross product between ax and az. Yeah, so as you know how to calculate the cross product between different unit vectors here, so to calculate the cross product between different unit vectors, so you can use this cyclic permutation here. Yeah. So we want to calculate the cross product between AX and AZ. So therefore, so we do AX cross AZ. So we should get AY. However, since when we go from AX to AZ, we are going against the flow here. So the flow is clockwise according to these arrows here. So when we do AX cross AZ, we are going against the flow. So therefore, we should get minus, because we are going against the flow, we should get minus AZ. So therefore, this will be equal to minus 10 times minus A. Oh, sorry, minus AY. So this is the cross product between U and B. Okay, so now we know the cross product between U and B. We can calculate the dot product between uh the dot product between U cross B and DL. So this will be equal to, so the cross product between U and B is just 10 AY, and then it will be dot with DL. So our DL is this one. Yeah. So our DL is DY AY. Then we should get, so if you remember, the dot product between the same unit vector should be equal to 1. Yeah, so therefore we just have 10 dy. Okay, so now we have the dot product between U cross B and DL. So now we can use this formula to calculate the EMF that is induced uh, in the conductor. So this will be equal to integral. So I will not specify the limit yet, so because I will explain this later for the integration limits. So now we have to just substitute here 10 dy here. So 10 dy. Okay. So now I want to talk about how to determine the integration limits here. So this is just, I put just some random number here, 0 and 1. It doesn't mean anything. So I will replace this later. So how do we determine the integration limit? Okay, so to determine the integration limit, so you know that there will be a current induced in the conductor here. So what you can do is you can first assume the direction of the current flow. So I'm free to choose any direction. So let's say I assume that the current is flowing in this direction. So the current that is induced in the conductor is flowing in this direction. So if I assume that the current is flowing in this direction, so what I need to do is I need to integrate from this. If I assume the current is flowing in this direction, I need to integrate. The integration limit will be from this end, which is P and P, to this end, which is Q. Yeah. So if I assume the other way around, so I'm free. At this point, I'm free to assume whatever current is flowing in this. So if I reverse, I assume that the current is flowing in this direction. I just need to replace this with, it will be from Q to P. Okay, so for now, let me stick with this one. I assume that the current is flowing downward. So therefore, so for the integration, I need to do the integration from this end to this end. So it will be from P to Q. Okay, so now for point P, so the y coordinate of NP is 0.4. So therefore this will be 0.4. And for this one, for this n, so the y coordinate is 0. So therefore, I just replace this with 0. And then if I do this integration, so should get, it will be 10, 0.40. So this will be y. So this should be equal to 10, 0 minus 0.4. Yeah. So this will be equal to, let me put this down. So this should be equal to, then will be equal to what? 0 minus 0.4 is minus 0.4, and it will be minus 4 volt. Right. Okay, so now what does this minus sign mean? So eventually I get this minus sign. So this minus sign here in the final answer here, so this minus sign implies that I have assumed a wrong direction of flow. So if I get a minus sign, so that means the direction of the current flow that I have assumed is wrong. But it is not a big, it's not really a big deal if you assume a wrong direction. So it just from, if you get a minus sign in the final answer, you know that the direction that you have assumed is wrong. So that means the actual direction of current flow is upward. So that is all it means. Yeah, if you get a minus sign. So that means that the direction of the current flow is actually flowing in this direction from this end to this end. So that also means that this end, because the current is flowing in this direction, so this end has a higher potential than this point. So this point has a higher potential than this point. Okay, so that is all it means. So let's look at another example. So we do the same thing. So first we need to determine the differential element. So you see that the rod is lying along the x direction according to this coordinate system. So that means this is dx ax, and then we need to determine the velocity vector. So the velocity vector, we see that the rod is moving along this direction. Yeah. So along this direction, according to our coordinate system, it should be along the positive y direction. And the magnitude is 20. So therefore, it should be 20 AY. And for the magnetic field, it should be 4 Tesla. And since it is oriented out of the page, so it will be positive A, Z, A, Z. Okay, so next we need to calculate the cross product between U and B. So the cross product between U and B is 20 AY times 4 AZ. So this will be equal to 80 AY times AZ. Right? So 20 times 4 is 80, and then we have the cross product between AY and AZ. So now to determine the cross product between AY and AZ, we can use this cyclic permutation. So we want to calculate the cross product between AY and AZ. So we do AY go to AZ. So we should get AX. And also because we are going with the flow. When we go from AY to AZ, we are going with the flow. So therefore we should get positive AX. So this will be equal to positive AX. So that is our the cross product between U and B. So next we need to calculate the dot product between the dot product between the cross product of U and B and DL. So this will be equal to AT C dot with, so ATAX here is the cross product between U and B, which we have just calculated here, and then DL here is DXAX. So therefore we get, so the dot product between the same unit vector, yeah, we have AX dot AX. So it is just equal to 1, the dot product between the same unit vector. So therefore we have AT dx. Okay, so now we can use this to determine the induced EMF. So this will be equal to the integral. So I will not specify the integration limit yet. I just pick up some random numbers. And then, so this will be equal to AT dx. Yeah, AT dx is this one, the dot product between U cross B and DL. AT dx, I just substitute this here. Yeah, I'll just substitute this into this. Okay. Okay, so now I want to specify the integration limit. So to specify the integration limit, I need to assume first. I'm free to assume whatever direction the current is flowing in this rod here. Okay, so let me assume that the current is flowing in this direction. I just pick up some random direction. So it can either upward or downward. So I just randomly, I assume that, so I don't know beforehand in which direction the current is flowing. So I assume that the current is flowing downward. Okay, so if the current is flowing downward, I need to integrate. The integration limit will be from P to Q. So it will be from P to yeah, P to Q, because I assume that the current is flowing in this direction. So the x coordinate for NP is 0. So therefore I just replace this with 0. And then the x coordinate of NQ is 6. So therefore this will be 6. So if I do this integration, so I should get 80 6x here. So therefore this will be equal to it's equal to 80 times 6 minus 0, which is equal to 80 times 6, which is equal to 480 volt. Okay, so if I assume that the current is flowing in this direction, so when I perform this integration, so I get a positive number. So what does that mean? Maybe you can have some interaction. So I've been talking for almost 2 hours. So can someone tell me? So I don't get, so in the previous one, I get a minus sign. Here I get a positive sign. So what does that mean? What does that tell you about the direction of the current flow?
It is correct.
Yeah, right, correct. So that means the direction of the current flow that I assume is correct. So the current is indeed flowing in this direction. Yeah, so that means this point has a higher potential than this point. Okay, so this one is pretty much the same. So maybe you can try this one, because I think this is a little bit different. So if you have time, we'll come back to this. But if time doesn't permit, later maybe we can try this as an exercise. So maybe I will focus on this one. So this one we have a, a square, I think. Yeah, it is a square conducting loop like this. Yeah, or rectangular or square. Oh, rectangular, sorry. It is a rectangular loop like this. So this length is different from this length. So this length is 1 meter and this length is 0.1 meter. And this loop, it is moving towards the origin. So meaning that it is moving in this direction. So meaning that it is moving in this direction. It is moving towards the origin at this velocity. And then the magnetic field is given here. It is pointing upward. Yeah, so it is pointing along the AZ direction. Now we need to calculate the total electromotive force that is induced in the loop, and then we need to calculate the current. So for this problem, so we need to divide this loop into sections. Yeah. So first, by the way, so this section will not produce. So this one, this section and this section of the loop there will be no EMF induced in this section and this section, because as I hope you can see this, because as the loop is moving, this section is not cutting the magnetic field. So I hope you can see this. So which is different from this segment and this segment. So for this segment and this segment, as the loop is moving, so this segment and this segment, so they are cutting the magnetic field. Whereas for this segment and this segment, as the loop is moving toward the origin, so they will not be cutting the magnetic field. So therefore, the VEMF for this segment and this there will be no EMF induced in this segment and in this segment. So therefore, we just need to focus on this segment and this segment. So let me call this segment as bar whatever, I don't know, bar 1 or left, maybe I can call it 1. Yeah, I think I can call it bar 1. So we just need we need to focus on this one first. Yeah, so for this one, so we repeat the same procedure. So DL is equal to, so this segment here, it is lying along, if you look at this coordinate system here, it is lying along the X direction. So therefore it will be dx ax, and then we have u. So u here, so the magnitude is given here, which is 20. And for the direction, so we can see that it is moving along this direction. So this direction is, if you look at this coordinate system, it is along the negative y direction. Yeah, so the positive y direction is along this direction, but the loop or this bar is moving along this direction, which is along the negative AY direction. So therefore, this should be AY, but we should put a minus sign in front because it is flowing in the opposite direction, in the negative Y direction. And then for the B, so this will be equal to tan Y A Z. Okay, so now we have all these quantities. We just need to calculate first the cross product between U and B, which is equal to minus 20 A hat Y times B is 10 Y A Z. So this will be equal to what is it? Negative 200, and then A Y times A Z. Okay, so now let's use the cyclic permutation here. So we want to do AY cross AZ. So AY cross AZ is AX. And since we are going with the flow, it should be positive. So therefore, this will be equal to negative 200 AX. Okay. Now we can calculate the dot product between the dot product between the cross product between U and B and DL. So this will be equal to negative 200 AX B dot with DXA X. Sorry, this should be AX. AX. Okay. So therefore this will be equal to negative 200 dx. So if you spot any, if I make any mistake in the calculation, if you spot one, please point that out so that I know. So yeah. So I think everything should be okay up to this point. Should be AX minus AX dx. Okay, and then we can calculate the VEMF. So VEMF here will be equal to the integral of this quantity here. The integral of this quantity. Okay, and so this will be equal to, so again, for the integration limit, I will first choose some random number. And then for this one, it will be minus 2 dx. Okay, so now I need to determine my integration limit. Yeah, so to determine the integration limit, again, I just assume whatever the direction of the current flow. So let me assume that the current is flowing in this direction. Just pick some random direction. So the current is flowing along this direction. So I guess a different color maybe. Okay, the current is flowing in this direction. So if
Sir,
yeah.
Y kat B tu tertinggal.
Y dekat B tertinggal yang mana
Negative 200 tu. Sebelum tu
Negatif
ada
ni.
Y, 10Y. Atas.
Oh ni, terima kasih, terima kasih. Okay, bagus. Okay, ni akan jadi sini kan? Ada Y kan? Betul?
Betul.
Okay, thank you. So this will be Y, so this will be Y. Right, thank you. Y. Okay, right. So this will be Y, and then for the integration limit, if I choose this direction, so that means this limit will be this point. So for this point, so the X coordinate is, so the X coordinate is 0.5. Here it is 0.5. And here it is minus 0.5. I need to make it more clear here. So if I extend the X axis here along the negative direction. Sorry. Oops. How can I cancel this one? Tak apa. Ni, kamu boleh. So hopefully you can see that here, not here. So at this point, so the X coordinate of this end is minus 0.5, whereas the X coordinate of this point is 0.5 because it is in the positive direction, whereas the x coordinate of this point is minus 0.5. So now since I assume that the current is flowing along this direction, so my integration limit will be from 0.5 to minus 0.5. Okay, so if I do this, I'll get minus 200y, and then this is 0.5 to minus 0.5. So this will be equal to minus 200y. So this will be x negative 0.5 minus 0.5. So that will be equal to 200. Sorry, that will be equal to 200 y, because 0.5 minus 0.5 is minus 1. And then if I multiply that with minus 200y, I will get 200y. Okay. Okay, so this is the EMF that is induced in this segment. But from this alone, I cannot yet conclude that the direction of the flow is along this direction. Yeah, so you need to remember, if you have a loop, you also need to next determine the EMF that is induced on this segment. Also, you also need to calculate the VMF that is induced in this segment. Only after that, only can you determine the correct direction of the current flow. So let's do the same for this side. So let me call that bar 2. So for bar 2, so DL will also, so it is also lying along, or it is also oriented along the x direction. So therefore it is dxax. And for the velocity, so it is also moving along this direction. So along this direction, meaning that it is along the negative y direction. So it will still be the same. But for the magnetic field, so it will be a little bit different for the magnetic field. Oh, okay. I think I forgot something here. So for this one, so you can see that this bar, it is located at 0.3. So the y coordinate of this bar is 0.3. So therefore we can directly substitute 0.3 here. And if you do this, in the final answer, we'll also have 0.3. Whereas for this segment here, for this bar, it is located at 0.4. Yeah, so therefore we can directly substitute 0.4 for the y coordinate. For this one, it should be 0.3. Okay, so now we can calculate this. So if we do this, we should get, so for this one, it is right. It should have y, but the y is 0.3, and for this one, the y is 0.4. And then if we do this, I think we should get 20 times 10 is 200, and then times 0.4 is, ada siapa-siapa boleh tolong tak? Ada berapa ni? 4 darab 80 4 darab 8. Betul? 80?
Betul.
Betul. Okay. So 80, and this will also be 80. And then here I have, so meaning this will also be 80 now. So I just substitute the cross product between U and B. Oh, sorry, no Y, right? So no y because I already substituted the value of y here, which is 0.4. So there will be no longer be y here, and this will also be 80. Yeah, because the dot product between the same unit vector is 1. So we have 80. And here I have also 80. 80, and this will be no y because I already substitute the value of y here, 0.5. So there will be no longer y. And now the integration limit. So to determine the direction, the integration limit, I need to be consistent. So I just now I assume that the current is flowing in this direction. So if you extend this, so the current is flowing in this direction for this bar, the current is flowing in this direction. And then if you continue this, so you will see that at this segment here, so the current, so you need to be consistent. So the current at this bar should be flowing in this direction. So just now I have assumed that the current is flowing in this direction. So therefore in this, at this segment, so the current should be flowing in this direction. So in this direction, if the current is flowing in this direction, so that means the integration limit will be from this point to this point. So this point is minus 0.5. And for this point, it is 0.5 because the current is flowing in this direction. So this is minus 0.5 and this is 0.5. So if we do this, yeah, so this will be 80, no longer y because I already substituted the value of y, and this one will be minus. Okay, and this will be plus, and this will be minus 80. So I hope I didn't do any mistake here. So again, if you spot any, if you notice any mistake, please point that out. So I think there's nothing wrong here. So therefore, this will be equal to minus 80. So there's no longer y. And for this one, it should be, if I multiply this, I should get 60. Yeah, so this one, because this one is 0.3. This is also 0.3. Okay. All right. So this is the EMF that is due to this part. And this is the EMF that is induced in this segment. So now in this question, so this is different from the previous examples. So in the previous example, we just have one bar. We don't have a loop. So therefore, this will be your final answer. Yeah. But for this one, if you have a loop, so to calculate the total EMF, so this is what you are asked to find here. So the total EMF, I can delete this one. So to find the total EMF, so what you need to do is you need to sum the EMF that is induced in all segments of the loop. Yeah. So therefore, so I write it here. So therefore, the EMF total, right, this EMF total will be equal to, so this EMF plus this EMF. So you need to sum these two. So if you sum these two, so I should call this maybe to be more, I call this I don't know, left maybe, left. So bar left, and then this is RIGHT, bar right. So the total VMF will be VEMF left plus VEMF RIGHT. Okay. So this will be equal to 60 minus 80, which is equal to minus 20. Okay. Okay, so this will be the total EMF. So I repeat again, if you have a complete loop like this, so to determine the so this is just individual EMF induced by in each segment, but the total EMF you need to sum all the EMF. Okay, so now the total EMF that we get is negative. So what does that mean? So I think it should be pretty clear. So that means if you get the total EMF is negative, so that means the current is actually flowing in the opposite direction as the current that you have assumed. So the current in the total loop, in the whole loop, is actually flowing in the opposite direction. Yeah. Okay. So that is how you do if you have a total, if you have a complete loop like this. So you need to determine the EMF that is induced in this section, and then to get the total EMF, you need to sum. And also you have to be consistent about the current flow. If you assume on this side the current is flowing in this direction, so you just extend this. So you can see that in this direction, the current is flowing in this direction. So why is it important to know the direction of current flow? So that will determine how you choose the integration limits. So I think we already 450. So I will not do this one. So maybe you can try this as an exercise, and also this one. So this one we just have a single loop, but for this one again, we have a complete loop. And so you need to calculate separately the VMF that is induced in this loop and also the EMF that is induced in this loop. And then eventually you need to sum the two. And if you, and also when you do this, so for each segment you need to determine the integration limits, you need to assume first the direction of a current flow. And then based on the final answer that you get, so you can know that whether the direction of the current flow that you have assumed is correct or it should be in the opposite direction. So I think that's all from me. So if you have any question, you can ask. And also here, so there's a, so probably I did some mistake in the calculation somewhere. I plugged in wrong numbers. Yeah, so maybe you can double check this, and also with your lecturer, with Dr. Rabiatun. So I'm sorry if I make any mistake. So you can double check this. Yeah, so but I hope you get the idea of how the procedure to do this. Okay. I think that's all from me, Dr. Rabiatun.
Okay. Thank you, Dr. Arif, for a great lecture. Okay, it was a pleasure to have you with us today. All right. So for the student, do you have any questions that you need to ask Dr. Arif?
No.
No.
No, madam.
No. Okay. All right. So I will give the attendance form in the chat box. Can we have a photo session? Can we have a photo session?
I have one question.
Oh, okay.
Okay, ada soalan.
We have one question
Yeah.
here.
Yang example 9.5 tu, 9.4.
Mhm.
uh,
9.4, 9.4. Okay.
Yang 3AY tu dia begini. Dia apa jadi?
Oh, so 3 AY itu kalau saya spend masa sikit so kalau kita expand, so if we expand this, so we have two terms here, right? Do you see these two terms here? So we have one, this is the first term and this is the second term for the magnetic field, right? Boleh nampak tak yang tu sebelum saya proceed? Okay, tak apa. So kalau kita expand this, so we will get, so this will be equal to, so I write this here. So this will be equal to B naught T square, which is equal to, and then 3 B naught T square A Y. So now if we expand this, so that will be equal to the dot product with pi times 0.1 square A hat. Boleh nampak tak setakat tu? Apa yang saya buat?
Nampak?
Yang tu nampak kan? Ataupun saya teruskanlah. Yang ni ia akan jadi 2, saya just copy yang ni lah. Dia akan jadi 2 AZ sini Okay, so we have, if we expand this, we have this two terms. Okay, for the first term here, so I guess from what I understood from your question, so you say why this is 0, right? What is that your question?
Yes.
Okay, so yeah, so right, so this is equal to 0 because, so if I write this explicitly, so if I write this explicitly, so you will see that this is actually equal to pi A Y C dot. So you see that this first term here involves the dot product between AY and AZ. So as you know, if you have the different unit vectors, so the dot product between different unit vectors is just equal to 0. So it is always like that. So if you have the dot product between AX and AZ, it will be equal to 0. AX and AY, it is equal to 0. So that is why this is equal to 0, because it involves the dot product between different unit vectors, which is different from this one. So this one, why it is not equal to 0? Because it involves the dot product between the same unit vector, AZ and AZ.
Faham.
Okay, good.
Okay. I think that's all for the questions, I think. Okay. Okay, thank you again, Dr. Arif, for the great lecture. So can we have a photo session? Boleh turn on camera tak? Sekejap, macam mana nak ambil gambar ni? Dr. Arif, you still share the screen? Okay, I print screen, Okay, one. Okay, next slide, next screen. Okay, thank you very much. Okay, thank you very much for joining us today. So a recorded video for this lecture will be shared by your group lecturer, inshallah. Okay, have a nice semester break. Okay.
Okay.
Alright, thank
Terima
you
kasih
very
semua.
much. Thank
Selamat
you,
bercuti.
Dr. Arif. Selamat.
Okay. Okay.
Thank you, madam.
Baik,
Thank you, doctor.
Thank you, madam.
Thank you,
Thank you,
doctor.
sir.
Thank you, madam.
Thank you, madam.
Okay.
Doctor.
Doctor.
Thank you, madam.
Madam.
Yeah.
Link
Madam,
attendance